traffic, but I'll try to mute it when people are going by.
Okay.
And hopefully when I'm talking, it'll be quiet.
What's going on at MIT?
There's a conference on economics and computation.
Oh wow!
Yeah, I'm excited. It's pretty cool. There's like not a single blockchain person here, which is great because I get to absorb like a different kind of culture.
Huh. So is it like traditional economics and computation?
Sorry, I somehow like disconnected and got reconnected. Is it like traditional what?
Traditional economics and computation.
Yeah, I mean it's there's like game theory and mechanism design actually mostly, like kind of thinking like I just was in a workshop describing algorithms for solving particular types of games, but there's another one on mechanism design going on right now, and another one on like big data and game theory.
Got it.
Yeah, it's kind of neat.
Cool. I don't know if you got my Skype yesterday.
I did. I didn't really have time to like digest and understand it. But I'm gonna review your messages soon.
Yeah, sure. No worries. And basically, all I was saying was that you can apply the reflective trick to your method of replication, and that will automatically be a form of sharding.
Right. Yeah. I remember. I just didn't understand it.
Yeah. Actually, after I wrote that, I noticed I was talking with Mike about it. There's a way that you can consider the whole thing as a form of a derivative, or it's reminiscent of a derivative. If you look at a type equation that mentions x, if you decompose it into contexts that, at least from the point of view of x, don't mention x, plus contexts that mention x once, plus contexts that mention x twice, and so on. So that's your type equation. And you can write down a new type equation in which you have closed off one occurrence of x in each of the different contexts by a recursive. You substitute for x the recursive closure where you tie the knot. So that reduces the occurrence of x by 1 degree in each context. So it works remarkably reminiscent to a derivative.
That's interesting.
Yeah, but it also produces this recursive type, right? Wherever you mentioned it, you now have this this recursive form, and that's that's, for example, how the row calculus is derived. If you think of the pi calculus as a kind of type equation that's parametric in the channels, and you close out the pi calculus by putting in a recursive form for all the places where the channel variable is mentioned in the type equation. That gives you the row calculus. So it's and you can see that automatically that's where the idea of namespace and everything else it comes directly from this idea.
Yeah. I don't actually have namespaces. I don't use namespaces for sharding. I don't. So I don't really 100%. The like namespaces like don't show up at all in my replication.
Yeah, I'm not saying that you're. Yeah, I'm not.
Which is kind of what I would like. What I would like to share, and something that you like mentioned, but we have actually, like, as far as the Casper stand-ups go, like it hasn't been mentioned at all. And so like anyone who's following doesn't really know, what you're referring to.
Yeah. Well,
You're
that's
saying like,
I was just kind of.
you can apply reflection to this replication.
Yeah, I was just hoping. I was just shooting the breeze until Vitalik came, but he didn't come. So let's get rocking.
Oh, okay, cool. So that's cool. I didn't realize. I thought maybe you were giving an update.
No.
Okay, cool. So I guess like like this is the start of the stand up now.
Yeah. So let's go.
So yeah, I'm happy to chat about research this week because it was like super exciting. Basically, I went to Seattle last week for about 5 days, and like three of those days, uh, I was hanging out with like you, Greg, and Kent, who is not on this call. And spent a lot of time kind of working on trying to apply the correct construction consensus approach using estimate safety to get consensus safety for a kind of arbitrary rewrite system or like reduction semantics, basically, a system where you kind of have like terms in a grammar with equivalence relations and reduction rules, and kind of developing a process for replicating this kind of abstract computational like theory. I don't know, how on point my language is, but somehow I'm really quite sure that I've solved all the kind of difficult problems for defining this consensus protocol. And basically, it's pretty neat because in some sense, because any kind of language can be written as like grammar, equivalence relations, and rewrite rules. That this is kind of like some kind of fundamental limit. I'm not sure that I'm done replicating stuff using the construction approach, but definitely this is kind of like one limit. I haven't say replicated a real number or like done anything with like arbitrary precision, but somehow replicating all of computation with concurrency is really cool. And basically the actually that's my favorite thing about this whole process is basically that it's highly concurrent, and I can take advantage of all the concurrency that is allowed to me by the rewrite rules. And so I kind of end up with this essentially fork choice mechanism on a concurrent schedule for executing rewrite rules, where like it doesn't matter if you execute the schedule one way or another. In the end, you get the same term from running all these rewrite rules. And so basically, there's like this kind of schedule choice process that is like very similar, actually, in the end to fork choice, only it applies to this concurrent schedule. And the kind of key thing to kind of to do is to write the reduction schedule in a way that kind of you can tell maps exactly onto the execution of the reduction rules, and also that displays the different alternative reduction rules that maybe have happened or have been proposed by different validators, so that they can engage in this kind of something like a negotiation process where they finally agree on a single reduction schedule for this kind of concurrent computational model. And it's pretty cool. Basically, the way that I like to describe it is that normally a blockchain is kind of like a puzzle where a block fits on top of another block if the prehash given in the block is the hash of the previous block, or the block it's going on top of. In this kind of concurrent schedule, the puzzle pieces are actually considerably more complex. They don't just fit on like one previous block; they fit on like maybe some number of them. Namely, they fit on top of the reductions that determine the state that is being reduced by this next application of the reduction. And there's a kind of, they fit really neatly on, they need to fit really like perfectly on top of each other. Otherwise, somehow, you're not applying the reduction to a state that, to the state that the reduction was like meant to be applied to. And so I kind of have this like concurrent. I call it a puzzle. It's really like a DAG of reductions. And I call it a puzzle because like the way that I check the validity of the DAG is by checking if they kind of line up in a certain way. And then basically the nice thing of puzzle pieces is basically if there's two conflicting transitions, they're not going to both be able to fit into the puzzle. And that's kind of like the base case element of the fork choice, where basically like you have two puzzle pieces that could fit on top of another one, similar to on a blockchain how you can have like two next blocks that fit on top of the previous block. Only slightly more complicated now, because instead of having just kind of a really simple puzzle that's just like kind of a single shape and a straight line, we have this kind of DAG, and you might have a puzzle piece that fits on top of multiple puzzle pieces that is conflicting with another puzzle piece that only fits on top of like one of those. So the data structure is a bit more complicated, but it turns out that the fortress rule is quite similar. You basically just use the weights of the validators and their latest messages to see which puzzle piece is in more of the weight schedule, and use like tie breaking on the weights to get rid of the kind of tie edge case. And so it's kind of very reminiscent of the binary consensus and the blockchain consensus. Only it's now applied to kind of abstract computational model. So that's kind of my main update, and basically the work that entails, like firstly like setting up the data structure, and then defining estimates and estimate safety, and then that kind of like fills out the whole correct by construction attack path, basically, because once you have estimates defined and estimate safety defined, the safety proof, so the consensus safety proof, is kind of complete, and then it's a matter of kind of implementing the estimate safety oracle, and then somehow the safety side of the protocol is done, and then the liveness side is a normal kind of discussion about like trying to make a safe state by like trying to make the shape of communications that correspond with the safe state. So it's pretty cool. I'm pretty excited. It was really cool to go from just to see a relatively small change from binary to blockchain to kind of abstract computational process.
Yeah, that's crazy.
Yeah, it's really cool, right? I'm excited, Karl, to see how much or how little the code base is going to change.
Yeah. Oh my God, that'd be insane. So the part about like parallelism and fork choice, I didn't actually I wasn't able to visualize like
basically what happens is that wherever you have opportunity for concurrency, all of the validators have to agree on the winner of the race.
So whenever you have a race condition, or like a two rewrite rules that kind of rewrite the same stuff.
Yeah. Okay. Cool. Wow.
So they all. I mean, you can have multiple different sort of logical threads, and in everywhere you have the potential for two threads to compete, all the validators have to agree how the competition is won.
That's right.
Okay.
Yeah, and the kind of neat thing is that like really the only case where this happens is where you have two conflicting rewrite rule applications. So basically, like we need to kind of like take a rewrite rule and sort of like memoize it to say in what context it's being applied in order to like construct this like puzzle piece. So it's kind of like taking a transaction and like maybe giving it some pre-block information. Or in a model where we have like genuinely atomic transactions, the transaction itself will specify what the previous state has to be. And so you kind of just from looking at these memoized reductions, we can tell whether they are conflicting or not, which kind of helps a lot.
Yeah. Cool.
Yeah. I think it's pretty cool.
Yeah, so there are lots of interesting opportunities, also lots of interesting places where things can where the protocol might fall down. But it's a lot more clearly specified. So that's a good thing. And what you can imagine is the K framework is a place where you can specify these kinds of systems much more generally. In fact, this week, Mike and I were speaking with Grigore Rosu, who is the principal researcher behind K framework. And anyways, you could imagine taking a K framework spec for a variety of systems and pressing a button, and it's automatically replicated. So it builds, the K framework sort of automatically builds an interpreter. In the case of the academic version of K framework, it builds a symbolic interpreter. So you can also do a bunch of other sort of formal methodsy kinds of things. And in the case of the commercial K framework, it more or less just builds an interpreter for the rewrite system in consideration. But you can imagine augmenting K framework with the replication mechanism, and you automatically get a replicated interpreter that runs in a distributed setting.
That's totally, I think, like, a really cool goal. I don't know what the difference is between augmenting it and piping the results, or like piping a K framework specification into a consensus protocol. I don't know really exactly what the difference is. To me, it just sounds like where you put the software. But
that's just a factoring. All I'm saying is, imagine that you start with a formal the thing that you need is just a formal spec, right? And from the input of the formal spec, you derive not just an interpreter, but a distributed interpreter, a decentralized.
Well, a consensus protocol. I mean, we don't need to.
Well, no,
call it just replication.
Okay, yeah, but the result of the consensus protocol is that you have a decentralized replicated interpreter. That's the thing that is interesting here from the point of view of the output of K framework. The interpreter is now sprinkled over a bunch of different machines, and as a result, is more robust, right? It has the potential to be more available. And then if you make it, economic, then you have this. You have a sort of turn the handle approach to generating a public economic compute infrastructure for any such spec. It's actually, I mean, to see the scope of the idea, it's actually super worth it to look here. I've got the GitHub, and you can kind of see the different specs that are available. Let's see.
Yeah, I noticed that there's
there's an EVM
people. Yeah, the IOHK people are working on the EVM spec in K framework, which is super cool. I hope that ends up being useful for us. Basically, it's going to be kind of boring if they only have like one transition and therefore we don't get any concurrency, or like a one rewrite rule that applies to like the entire state.
And that's
the entire term.
That's more or less what they've got, right? There's nothing, but you can kind of see. I mean, it's sort of interesting again from the point of view of just the more broad application here. So they've got Haskell, C, LLVM, JavaScript, Java. Let's see, what else have they got? They've got some interesting ones. OCaml, Python, right? So these are all different systems that have specs inside K framework, to some level of completeness or another. So now imagine that you augment K framework with this consensus algorithm generating algorithm, which is is what is there. And then you is what Vlad was talking about. Then each one of these semantics, what K-framework does is it eats one of these semantic specs and it generates an interpreter.
That's super cool.
Right. I mean, it'll do more in the case of the academic side, but it's super slow. It's not, you know. It's not,
so can you explain, you know, what an interpreter does other than just like kind of apply blindly the reduction rules, or like just do it in a particular way, or?
they don't have strategies, so it's going to apply whatever it can figure out to apply.
So all it basically does is just apply the reduction rules that it has available.
It applies the reduction rules that it has. I mean, there's in
a deterministic way or in a non-deterministic way.
Well, it's going to be deterministic for all the systems that are deterministic or confluent, right? So
yeah, what I mean is, like, you know, if it has a choice between like applying reduction rule 1 or 2, will it always apply 1 first? That kind of, that's good.
Again, I don't know enough about their structure. I know that they're trying to add strategies, but I don't believe that they have that in place yet. So there has to be a reduction strategy. Like even in the case of, you know, sequential systems where you have you know, a choice, sometimes the choice can lead you to divergence, right? Like famously in the lambda calculus, right? There are different reduction strategies, and different reduction strategies lead to different divergence, right? So anyway, but you know, I encourage people to go look at K-framework and find that out. But you can imagine, you know, taking the algorithm that Vlad has described earlier and applying it to K-framework in such a way that for each one of these, you automatically derive a decentralized, distributed version of the execution of the interpreter.
And then will those share bytecode or something? Like, will I be able to message across, like if I have one of those VMs for Python, will I be able to send messages to one of those VMs written in C or for C?
No, it's for each one, you know, you can talk to it in its own, you know, language. That's sort of, they don't have cross language capabilities. It's, you know, one spec doesn't talk to another. Now, you could probably cobble together a meaningful way in which one spec can talk to another, because now they're all written in the same specification format.
But right. in the end you would need like a new reduction rule that handles communication of this new bytecode.
Yeah, I mean, in general, the way that's going to be done is you have some translation of one model into the other, right?
Right. I was just thinking you could probably expose a pipe, like a data pipe that would be shared across all of those VMs, right? Like a
so do you mean like, you know, add a new reduction or use one of the existing reductions and pipe things through there?
I mean, creating a common reduction that's preserved across all of them.
Right. Yeah. Well, it's something that, like, you know, only passes messages around.
You're right. Exactly. Just passes bytes back and forth, and then the deserialization of those bytes and the validity of that deserialization would have to be done in the other.
Yeah.
Am I getting that right?
And yeah, that makes a lot of sense. And then everyone could kind of like implement their own kind of serializer, deserializer for this, basically this binary interface.
Yeah.
So anyway, it's kind of an interesting idea.
Yeah, it's super cool. And the another nice thing about this system is that it does kind of provide us some hints for moving into sharding because of the whole concurrent schedule thing. You could imagine that, like, what we want to do is, you know, shard a general abstract computational system, and somehow that might provide a little bit. It might be a little bit nicer to reason about than adding concurrency to the EVM. You know, instead we can kind of like ask, so like Martin Beasy or someone to like who's working on the concurrent EVM thing to say like, oh look, just give me a reduction semantics for the new EVM, and then I can work on that, rather than having to like myself look at the actual concurrent execution model when I'm thinking about sharding. I can just think about sharding and abstract computational environment.
I don't quite follow that argument.
So right now, when I think about sharding, I also am thinking about the computational model. I'm not like, and it's part of the sharding problem statement. Whereas now I can kind of remove that from the problem statement. And
No, I
say, okay,
understand.
the set of
I just
statement.
don't understand how you're doing it, right?
So basically, my kind of assertion that I'm relying on is that like there's going to exist some kind of like formal spec for whatever concurrency like is the best for smart contracts, and like that spec could be specified in terms of one of these like abstract computational models, and therefore as long as I can shard an abstract computational model, I'll be cool.
Yeah, but that means basically you're fundamentally changing the VM that executes the contracts.
Yeah, but well, that's true. I mean, but I'm also black boxing it, so the change could be backwards compatible. It could be, I'm kind of black boxing it, which I think is, I think cool in some way, because I get to like factor out the problems in a different way, in a way that maybe it's like easier to deal with.
Possibly.
like I mean, one problem is how do we make a backwards compatible concurrent EVM. And then another problem is like, how do we shard an arbitrary computational system? And then I can kind of bridge that gap by asking for a formal spec of the concurrent virtual machine.
Well, I mean, you could have done that anyway, right? I mean, you know that consensus works on whatever your state is, and you know that.
Yeah, but the idea is that like for sharding, I don't need to necessarily like as a part of the consensus level thing think much. Hopefully at all about the actual VM's semantics.
No, you will, unfortunately. That part, the sharding is all about the concurrency.
Of course, but I can just handle it through the abstract interface, as opposed to handling it like by specifically thinking about things like gas, the various things in the EVM.
The gas is all going to apply to the reduction semantics of the.
Yeah, exactly.
Right. So all of that.
So I'm going to be able to look at it only through the reduction semantics.
Right. But I agree. But that's where it had to be always. Your fundamental model for the VM is the thing that's going to impact your.
Yeah, but now I don't need to think about like on a case-by-case basis how different concurrency models will impact the VM. I can just think about sharding an arbitrary model.
Yeah, well, let's maybe we can go deeper at another point. That's a longer conversation. We have a few other people that probably need updates.
Karl?
Sure. So basically, I spent the last week tackling issues with the validator and making sure that they all like stay in sync and pass messages properly and assign messages properly. And so it actually turned out to be a little bit more complicated than I had originally thought. An update on the blog post. I wanted to make sure that like when I release the Casper blog post, that it kind of is done in a with kind of like due diligence sort of way. And so I now know I'm going to release it, but I haven't actually done it because it kind of took a backseat to all the research. Unfortunately, that's seems to be like the trend of communication taking a backseat to actual like work. But I guess I will definitely do it for next week, because I think it is important and I should prioritize, even if I have coding work left to do. And then lastly, there a kind of tiny update is I spent a little bit of time thinking about the how to kind of model the outcomes of token sales, and so I came up with a just kind of simple framework for thinking about like just plotting the outcomes, which is actually super straightforward, and then just considering like what is the utility function of all the different outcomes for the token launcher organization. So basically that's my update.
Neat. So what is the token launcher? Oh, sorry, I didn't.
I mean, I can show you some horrible graphs that I threw together, if that's interesting.
Yeah, I mean, if it doesn't take too long, you share screen.
Sure.
That sounds potentially
Sure. So
interesting little.
yeah, it's a little diversion. It's nothing. These are the like least scientific charts in the universe. Essentially, it's just you just like chart it percent of tokens remaining versus the ETH raised, right? That's kind of like those are the two kind of choices that you have to make, right? So a fixed price, fixed cap. So this just represents all possible outcomes of the kind of token launch, right? So this is a fixed price, fixed cap where there is no minimum. So essentially, if they they could technically sell 1% of their tokens and raise 1,000 ETH in this case. And so these are you follow this line. And you can say like because like the actual organization that wants to do this, they like really like they think that this is perfect for them, and then maybe they think that this is like this. I'm kind of just quickly kind of throwing on a utility function, and so they can say like, oh, like utility heat map kind of. So they can say like this would be the best success for our token launch. This might be okay. This would be fine, right? It gets the darker it is, the better it is. But then like all of this would be terrible, right? They just raise a little bit of money and give up a little bit of their company, but it would look bad, and they don't like that. And so you can do this also for a reverse Dutch auction. So this would be kind of the percent, the amount of ETH raised in this reverse Dutch auction format is always fixed. If they don't raise this much ETH, then they will just give it a return all of the total funds. And then so essentially this is the kind of reverse Dutch auction where you vary the percentage of tokens that you're giving away. So here it's like starting at something like like 99% or something, and it goes down to 70%, always raising 3,000 ETH, right? So this is like, and so maybe this is, you can argue that this is a little better. You can say like, oh, we like anything around here, and it gets like some kind of utility function that looks like this or something like that, right? So this kind of better covers this is fewer bad outcomes than the first one. And then if you can even like combine reverse Dutch auction with a fixed price, fixed cap, where you get this like reverse Dutch auction right here, and that sets a target price, and then you can just like do a fixed sale at that price, right? And so what that would kind of look like is if you sold all your tokens at the kind of 99% mark, then you'd have this fixed price, fixed cap all the way up to selling 70% of your tokens. And so then you can, at every point, you get a new possible outcome for all of the different like token prices, and you get this like way to cover more ground in terms of like possible ETH raised versus percent tokens sold. So anyway, that's kind of the overview.
Cool. Yeah, I feel like lots more could be done, Karl.
Oh, I agree. There's a I think this one, like many things that are not covered in this model, is like one thing is people want to guarantee some kind of return on their investment. So and if they for the like early investors, right, they don't want the token to like in the token launch sell for X and then afterwards sell for X minus 0.5 times X. So what that like that portion of the utility is never represented with the way that I'm modeling it, but it at least goes and starts going in the right direction.
You also don't do any kind of safe token sale mechanism. There's have you looked at maybe trying to visualize the dilemma trilemma thing?
Yeah, that's a good point, actually. Yes, I should. I haven't actually come up with a bunch of the actual graphs. So yes, I will do that. That's next on my list.
Sweet. Anyone else have an update?
Well, Mike and I both have updates.
Great. Yeah, we'd love to hear.
Mike,
spend a bunch of time talking with Vlad this week. We got to a point where I think I can understand the correct by construction idea that he's been working on, as well as been writing up some of the stuff from our conversations. So once we get a wiki up and started, I'll have some content for it. And then
Where were you guys going to put that wiki? Sorry to interrupt. What were you thinking?
on our website.
Oh, for our chain, you mean?
No, we were going to maintain it on the PyroFX website.
Oh, okay.
And then you can link to it from our chain if you like. And then got a paper written, and Greg got a paper written that we submitted this Friday. Or I guess I got one written from scratch and Greg updated one that we had written earlier. I'll let him talk about that one. But mine one was explaining the ladle algorithm. We'll see whether they accept it. I didn't have the time I needed to add all of the proofs. But maybe they will. It's an interesting conference.
Mike, did you put it up on archive?
I haven't yet.
Okay, cool. So we can put it up on archive and then people can read the draft.
Yeah.
And then, was there anything else?
Just that.
Cool. So in addition to doing the work on with Vlad and kibitzing with Mike about the ladle algorithm paper, I updated the row combinator paper for submission to Express SOS. Yeah, so basically in the last rounds of reviews we got, looks like this might be right, but what's the relevance? Why is nominal phenomena interesting? And so we just basically made reference to a bunch of the literature that why the nominal problem is hard. Mike found the Popplemark challenge that mentioned that binders is one of the key features in language design. And frankly, it seems like so well established that nominal phenomena is subtle and hard that I didn't think we needed to mention that, because it's now like 10 years of papers on exactly how hard this is. But anyway, so we referenced that, and then
do you want to describe quickly, like why binding phenomena are important?
Well, I mean, basically anybody who's ever written a function knows that a function takes parameters, and then they know that the change of variable names in the function makes shouldn't make a difference to as long as you do it consistently, shouldn't make a difference to the execution of the function, right? That's a concept that every programmer is familiar with. That concept is called alpha equivalence, right? And in general, what you'd like to be able to do is to reason about a phenomena like alpha equivalence. And another one, imagine that you probably many programmers are familiar with the idea of reference passing, right? So if I create a reference to something and then pass it outside of a scope, what happens? What happens to the reference, and what happens as the state is mutated, right? So that also turns out to be quite a subtle phenomenon, and a lot of programmers get it wrong all the time. So being able to reason about those things in the abstract would be awesome. So if you go, for example, and you look at K-framework, just because we were just talking about that. So K-framework doesn't deal with nominal phenomena in a clean and modular fashion. It sort of is a little bit hand-wavy about exactly all of that stuff. And so modularizing that and abstracting it to the point where it could be treated as a unit, like names, your names or variables unit for your language is an interesting problem. The reason we were looking at the particular approach that we looked at is because there has been an approach based upon a relatively obscure form of set theory called Frankel-Matofsky set theory, where you consider sets not just built off of the empty set, but sets built off of a supply of atoms, where you don't have any clue about the internal structure of those atoms. You just know that they have to be there have to be at least countably many of them, and and they have to enjoy a kind of swapping or symmetry property. So if all the sets that you built off of a particular subset of the atoms have to somehow be the same as sets built from a different subset of the atoms that sort of can be thought of as a swap of one subset for the other. So axiomatizing that, you get a notion which is very, very close to the idea of alpha substitution or alpha equivalence, and you get a notion which can faithfully interpret the fresh channel and construction of the pi calculus. However, the apparatus is interesting because from the point of view of like actual real modern computers, an infinite supply of atomic gadgets, which you don't actually have any understanding of what's going on inside, is not realizable in a modern computer. So there are workarounds for supplying things like this. Well, you could pretend that a finite supply was an infinite supply, and that works up until your compute power grows to the point where you can exhaustively explore all that finite supply. We've had that happen many times in the past in computing. The other approach is that you take some effectively representable set as your supply of atoms. So, for example, the natural numbers. But the reality is that effectively, so the natural numbers are great, right? Because they have internal structure, and with a single recursive equation, you can specify all that structure, right? But now you run into a little interesting conundrum. The conundrum is, well, what notion of computation did you use to effectively represent that infinite supply? Because if that notion of computation has any binders in it, well, then you haven't made any progress. Right. There's a little circularity there. And so and that was the origin, in some sense, of the reflective version of the pi calculus and many other reflective phenomena that I discovered over the past decade or so. And the reason that's related to everything we're talking about here is that the ladle algorithm works on things called Levere theories. And Levere, you can think of K-framework as, basically working with graph-enriched Levere theories. So the Levere theory part of a K-framework spec is effectively the grammar for whatever system you're working with. If it's a spec for Haskell, so it's the spec for the grammar for Haskell. That's what a Levere theory codes up for you or captures. And then the rewrite rules, well, effectively, you can think of the rewrite rules as generating a graph, right? It's the DAG of the evolution of any particular term under the rewrite rules. So that graph is the graph-enriched part of graph-enriched Levere theories. So Levere theories are not strong enough in themselves to capture nominal phenomena. So you kind of have two options here if you want to increase the scope of the ladle algorithm to deal with practical languages like Haskell or C# or whatever. Either you can come up with things called nominal Levere theories, and those things do exist, but then the calculations get a lot more complicated. Or you can see if you can just evaporate all the nominal phenomena. You can compile all the nominal phenomena down to something that doesn't mention binders. And the question is there any evidence for being able to do that? Well, yes, there is. There's a name-free account of the PyCalculus called the SKI combinators. So you can get rid of lambda abstraction by compiling it down to this set of combinators that doesn't use variables at all. And so now the question is, could you do that in a wider scope, a wider framework, like calculate for concurrency? So it turns out that Yoshida attempted a combinatorial representation of the PyCalculus and couldn't get rid of the new binder. And in some sense, that was motivation for Gabay and Pitz's work on the nominal set theory, because the new binder seemed a lot more fundamental. And then Matthias Radestock and I showed that you can get rid of new entirely if you use the reflective techniques. So that's the relevance here of this the row combinators, is showing that you can get a combinator set for concurrency that's like SKI. So it's kind of an SAT analogy, So lambda is to SKI as pi is to what. And so we provided the answer for the what. So it's interesting in its own right because it's the first name-free combinator calculus. However, for concurrency. But it's more interesting in this larger context that Mike was describing, because it allows us to extend the ladle algorithm for generating the type systems to a much wider set of rewrite systems. So now, going back to that idea, I'll just close up my little spiel here. If you go back to the K framework thing, here it is. It's that. So if you go back to this, so you can imagine an enriched K framework, which does two things. One, for any one of these, C, EVM, JavaScript, any one of the WASM, LLVM, Rolang. So you write down one of these K framework specs and you generate two things now. You auto-generate a type system for this thing, and you auto-generate a consensus algorithm for this thing, right? So now you literally, all the language stuff, all the compute stuff, and all the consensus stuff is completely commoditized. You press a button, and out from your spec is a typed, distributed calculus, right? So
that's the goal, anyways. Yeah, and it
well,
seems
with
more and more
with
doable.
respect to the Ladle algorithm, this is not just a goal, right? We've got the algorithm described. We know how to do this, and we're in the midst of prototyping the algorithm on top of K framework right now, right? That's
Sure. It's still a goal. It's not like a far goal. It's not like there's like less miracles that need to happen. But it's
yeah,
still,
that's correct. Right. But yeah, but I believe that it's an important goal, and it's a goal that's entirely reachable now as a result of the work that we've been doing over the last couple of years.
Okay. But actually, when you just mentioned the kind of like term crank, process of turning like one of these calculuses into like this distributed thing, you didn't actually mention again the nominal phenomena. Another quick question I have is like you mentioned also that nominal phenomena are useful in programmers, but you also mentioned to me last week that the combinators can lead to some kind of complexity blow up.
Yeah,
I'm not really
that's
sure
exactly.
how to reconcile.
Yeah, so that's exactly right. I mean, the good news in all of this is that lambda abstraction, having parameters to your functions, adds very, very useful expressive power. When you get rid of lambda abstraction, or when you get rid of having functions with parameters, you get a combinatorial explosion, right? So for those people who don't.
So when you're able to like factor out the nominal phenomena, do you still get to avoid that computational explosion?
Yeah, that's kind of the whole point. The whole point is that you can safely add in your names and know that your type system generation and all of that stuff just works, right? That the point of this is not to compute on stuff that's name free. The point of this is to compute on stuff that has names and know
do you have like a type for names in this kind of combinator replacement for names?
So yes, you do, right? I mean, that was kind of that was what the namespace logic does, is it gives you types for names. That was the interesting thing. Is you now have this way of talking about names, and then it turns out that the way of talking about names links up with all the work that people have been doing on linear logic and region analysis, which gave rise to separation logic and all of that stuff, which is at the heart of the proposal for using namespacing as a way to deal with sharding, right? So there's like now 20 some odd years of region analysis research that uses namespacing and to talk about sharding, right? That's the whole separation logic stuff. And what the namespace logic approach does is it says, well, hey, if you just put the structure on the heap, on the addresses in the heap, in a way that you can reason about it more in a more regular way, then you get all that goodness that you've been thinking about for 20 years in an automated fashion. So yeah, that is exactly the idea.
Yeah, so it sounds really cool.
Yeah, it's a lot of fun.
Yeah, I wish I understood this namespace stuff more, because I feel like I'm kind of lacking. But it's okay. I'm sure eventually.
Yeah.
If you understand the idea of a type of a term, then you just extend that through quoting to the names, right? Because every name is just a quoted term.
In the row calculus.
Yeah.
Well, but more generally, I mean, kind of the whole point of the reflective technique is that it's super general. It's very abstract. I mean, like one of the points I make in the paper, and I've made it many times before, is that you can apply the technique to set theory. So for example, you can completely get rid of the whole FM set theory idea using the reflective techniques. You say, well, where do the atoms come from? Well, what if you had two different copies of set theory? You had red set theory and black set theory. And then you just have the element of relation over on the red set theory side. It can't see into black sets. Okay. And then over on the, from the red set theory side, black sets are atoms. And then on the black set theory side, the black element of relation can't see into the red sets, right? So from its point of view, red sets are atoms, right? And so now the two set theories are recursively interwoven in a reflective manner. This is exactly the same, right? It's exactly the same idea. And now you get FM set theory for free by applying the reflective technique.
For free, meaning without names, without atoms.
Without atoms, yeah. I don't have to pay. So Gregory Chaitin, who's a famous logician and computer scientist, so he talks about, your axioms as your risk in your theory. It's the part that you go, well, I'm not going to prove this. This is self-evident, right? That's the risk. So from the point of view of theories that depend upon atoms, right? You're adding, and especially accountably infinite supply, you're adding risk to your theory. When you apply the reflective techniques to eliminate that, you're eliminating the risk in your theory, right? So this is it's a nice trade-off. But anyway, we're over time, but that was all good fun. And thanks for the good fun in Seattle this past week, Vlad.
Yeah, no, I had a really nice time. It's too bad I can't be in America for a little longer, but I'm going to be back July, and I don't know, I might stick around longer. I'm trying to keep my plans open so that I can make a last minute decision.
Okay, well, I'm going to be in Berlin in July, first and second week.
Okay. First and second week I am in Europe, so there's a chance that I might drop by Berlin, but I have no plans to do so yet.
Okay, cool.
Sweet. Fun meetup, everyone. Fun stand up.
Yeah.
Yeah, as always.
Cheers.
Cheers.
Talk to you guys next week.
Bye-bye.
Bye.